This time I have a bit of a longer talk, so this is great. We can go through a few things. So I'll just go through the intro of who I am, roughly. So I am a DevRel/machine learning engineer at Superlinked. Maybe some of you have heard of Superlinked, maybe not. If not, you will hear more in the next few minutes. I've done some work in ML, like for biomedical stuff. I've done electrical engineering as my degree, did some more traditional data science work. So I've been kind of around the space. And that kind of mix of experiences brings a perspective within search that I think got me into doing a lot of interesting things. And today I'll walk you through some of these. And you may have seen this as the title of my talk. And this was in the agenda. And it sounds maybe a bit straightforward. But I think what you can notice here is that it includes BM25 and then something else called Mixture-of-Encoders. So this talk is a bit of like a timeline, like it has some historical context in a way. So BM25, the past, the traditional, the golden standard, and then we go to something called Mixture-of-Encoders, which sounds new. We don't know what exactly this is, but it sounds a bit of exciting. Also, it mentions next generation. So in this kind of with this idea in mind, with this sentiment in mind, I will do something of a, let's say I will tell you a story in a way. So to start with, what does this film and also a book, this one, and also this one, which is not a movie but literary book and one of the biggest kind of key titles in literature. Who has maybe read the Divine Comedy? Raise of hands. Okay, nice. Probably not the question you expected in a search conference, but hey. So what do all of these things and like media creations and literary works have in common? They're all trilogies. So what that means is an old Greek word. Well, I guess all Greek words are old because of the history, but anyway. So it's a story of 3 parts. And I was inspired by this. So basically today, I will tell you a story in 3 parts also. Probably not as brilliant as any of these works, but I'll try to make it interesting. And also, hopefully, unlike in the Divine Comedy, you won't feel like I'm dragging you through hell. But what I do hope, though, is that at the end you'll feel like you've been in paradise a bit. So that's the idea. And this is my story in 3 parts. I will begin first with what did DeepMind have to say about Superlinked's Mixture-of-Encoders. The second one is, what is this Mixture-of-Encoders thing I'm referring to? And the third one is, what happens with text-only benchmarks and evaluations? Are they enough? My idea is that they're not. So let's start with the first part, the intuition behind all of this, the intuition behind the main part of my talk, but also related to kind of something that's been current in this space, people have looked into, and there has been, let's say, some activity around this. So what did DeepMind have to say? Well, they actually haven't said anything, at least not yet. But I will speak a bit about them, or a specific paper that was launched in affiliation with them. So you probably have seen this paper. A lot of people were speaking about this on LinkedIn, on Twitter, well, X. But yeah, the idea is that this kind of got quite popular in the search community, and it explores some ideas on embeddings, theoretical limitations, and what this means for the whole search community. And I saw that, in a way, the conclusion that a lot of people made was this here, that sparse BM25 is the best. All these dense embeddings, new stuff, they're not that good. We want the old stuff. They're the best. So, okay, fair enough. A very dramatic, I guess. Okay, interesting. Are we back, or was this too? Yeah, DeepMind affected my ability to, yeah. I spoke too soon. So maybe I'll try to reconnect. But anyway, the idea is that this paper was mentioned a lot, and a lot of people kind of did this. Yeah, are we having?
I don't know. It looks like my laptop is not loading the presentation.
Are we? Yeah.
Disconnect from the Wi-Fi.
Maybe? Or the Wi-Fi is. Okay. So it's.
Maybe it's the
this
Wi-Fi.
is, yeah. Or.
So we can put you in our Wi-Fi. Can you?
Yeah.
Any other networks?
Yeah. Which one?
Then
Or this?
The PS Reg disk. PS Reg disk. This one.
This one. Okay.
Can I type it in?
Yeah. So while we're having this password edited. Yeah. But it comes in later. It's not at the start. It's. But this gives it a dramatic pause.
We're connected.
Yeah. Okay, we're back. So if I had a presentation which was 10 minutes or 20, probably this would have been the only slide here, and then I would have said, okay, thank you, this is the rundown of the paper, and then I will go into introducing what Mixture-of-Encoders is and go to the other parts of my story, of my divine comedy. And this is properly like just ChatGPT generated. And you've probably, this is just for people that haven't read the paper, haven't heard about it. However, luckily or not, I have a 45-minute talk today. So we will do something else. We will talk about sign rank theory and Hadamard matrices. So why am I doing this? I think this was a little kind of angle of the whole paper that maybe went unnoticed. So I wanted to build up from here and then state my point and then talk about kind of our angle or approach or what we're trying to do, but in relation to what happens in this paper. So how many of you have heard of like Hadamard matrix or like error corrections and stuff like that? Okay, cool. So this basically is a old communications theory idea from the 70s, I think, maybe even earlier. Some of these theories were there. And in a lot of these situations where there was radio transmission and all sorts of noisy channels, there was this way of doing error connection so that the signal goes through and there is this figuring out which bits are pair bits. So there was this cool kind of period of time where resources were low, so people had to be smart with how they were using them. And actually this theory, sign rank theory, originates from there, from those use cases where there is a corrupt channel and you had to transmit information and you had to make sure that, okay, there is some way of figuring out for me that even if the channel is corrupt, I can figure out what the end message is. And there is a lot of math here. And one kind of famous example is this Mariner 9 space probe, which actually used kind of like an error correction code based on this Hadamard matrix. So what is a Hadamard matrix? We have the photo there of, it's an old lecture, I think, from MIT that has this matrix. So it's basically this matrix that has very good row independence, which means if you can see all of these rows, 1 to 4, if you took any pair of these rows, so like if you took 1 and 2, 1 and 3, 3 and 1, whatever, you could see that there is an overlap of exactly half. So row 1 differentiates to any other row with half of the items. So it's like plus, 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 then the other one is plus, plus, minus, minus, for example, if you compare 1 and 3. So it's like a 50% overlap. And this makes the Hadamard matrix very useful in error correction because it's prone to noise. This kind of big difference in the row pairs, this orthogonality, is very useful when you want to represent stuff that are in a noisy channel and you can kind of miss out things. However, this is bad if you're doing something like embeddings or like what we're doing. And the reason is that you need a lot of dimensions to then represent your data. So one mathematical theory that kind of tries to look at these dimensions and orthogonality and how these rows differ from each other is sign rank theory and computing sign rank. And this is actually a very difficult problem. In fact, it is an NP-hard problem. So figuring out what the sign rank of an arbitrary matrix is, there is no algorithm of solving this. So what people have done is they have calculated this for some kind of famous matrices or patterns of matrices, and then use this to kind of extend and expand on this theory. So basically, what this means is that if in your matrix you find a pattern that resembles slightly this Hadamard matrix, you can say, aha, this matrix that I have will probably have a very high sign rank. For the Hadamard matrix, it's proven that this is n over 2, so half basically, which means that it scales badly in high dimensions. So if you have 1,000, you need a lot of dimensions to kind of represent this data in a way. And that's not good for embeddings. So in simpler terms, without kind of talking about sign rank theory and so on, I try to give an example that's a bit simpler, but illustrates this point quite perfectly. So but we're still standing, that's the whole point. Okay, we're back. So let's imagine you have 3 documents and 2 queries, right? So we're looking at cosine similarity, that kind of thing. So we're trying to match, okay, query 1, it's similar to doc 1 and doc 2. However, if we're trying to do this in 1 dimension, if you can see the left drawing, there is no way of arranging these queries so that they properly include the relevant document. So if we look at this as like a flashlight trying to capture the relevant documents, and that's the illustration of the dot product and cosine similarity visuals. The idea is that you cannot represent this in 1 dimension, right? This is a specific example. You have 2 queries, 3 docs. It's impossible if you have multiple docs for each query. What you have to do is you extend the dimensions, you have a 2D plane, and then it works perfectly. Query 1 captures documents 1 and 2, query 2 goes to docs 3 and 2. Amazing. So this is the key insight. This is the more visual explanation of this sign rank theory. It basically gives us a number of what is the minimum number of dimensions we need to have in order to represent this data. If we don't have that, we're unable to represent the data, have enough context, and so on. So as it says further down here, maybe you can't see, so the minimum number of dimensions required to encode a yes or no relevance pattern. So why is it a yes or no relevance pattern? Because it's a sign rank. So you saw that +1, -1. So that's like yes or no or relevant, irrelevant. So in this paper, what they do is they have this relevant, irrelevant. So that's the yes-no pattern. And now let's go into the theoretical bit, or more math heavy. So this is from the paper. I'm just going through it a bit. So what they do is they start with this binary relevance matrix. So quite simple. You have 1 if a document is relevant to a query, 0 if not. So it's like a query document matrix. And you have ones where the query is relevant to the doc, or actually the doc to the query, and 0 if not. So they start with that. And then they go to the next step and they say, because of our very good theoretical understanding of communication systems and theory and sign rank theory, we've decided to apply sign rank theory here. So they transform this matrix by using this 2a minus 1. This is like just a way of transforming the matrix so that the sign remains and all of that. So they end up with this sign matrix that you can see there, which is plus, plus 1, minus 1, minus 1, plus, plus. So this is just an arbitrary example. And then what they claim and they prove is that the sign rank of this matrix, so what we discussed just before, basically the minimum embedding dimension needed to guarantee what? To guarantee that all the ones, so all these relevant docs, because we have ones as relevant, 0 as irrelevant. So this, they want to calculate the minimum number of dimensions that guarantee that each one or each relevant doc gets placed or gets scored strictly above all of the irrelevant docs. So that's the requirement. They want to show that, okay, all the relevant docs are placed or ranked above all the relevant ones. That's the key here. And what they prove is this inequality down here, which states that this rank, which is called row-wise ordering rank, is bounded between the sign rank of this matrix, which means, so this is the by-the-book definition of row-wise ordering rank, which means the smallest embedding dimension D, such that there exists a D-dimensional scoring system that achieves this ordering for every row simultaneously. But the idea is that, okay, can we actually see that the minimum number of dimensions needed, they scale as the sign rank of the matrix scales, which means that if you go very far, if you increase the dimensions very high, you'll have a problem at some point. So to conclude, what does the math mean? Basically, it means that if you have this combinations of relevance, so this relevance pattern of like ones and zeros, relevant, irrelevant, and so on, there is a dimensionality limit. And at some point, no matter how good your training is, your embeddings, your embedding model, you cannot simply represent all the relevance patterns. No matter how well you train, you cannot do it. And that's the conclusion that they prove through all the math that I described and all the details in the paper. And what Kowalski says here is that single dense vector embeddings could use some help. That's the idea. That's what we're trying to do. This is how they've done this. So this is actually like an empirical way. So I talked about the theory. So they're doing the math, and they're describing things. But they also actually said, okay, we'll build a data set and prove this to you. It's not just theory. And they build this data set, which closely resembles the examples I spoke about, where there is this kind of random attributes, and there is this queries and documents, and there are all of these combinations of different people that are relevant to different queries, as in who likes apples, who doesn't like apples, and stuff like that. And they tested this data set by using state-of-the-art embedding models from MTab, and they saw that, okay, actually this problem persists at scale. So this fancy dense embedding models cannot represent this very unique combinations of document relevance pairs. So this is the conclusion here. And now as I'm approaching to the second part of my story, I'll talk a bit about, okay, what's our angle to this? How are we trying to alleviate this problem of not being able to represent this combination of relevance pairs? You saw maybe one of the queries is who likes quokkas, and this is this cute animal over here. That's what this means, which I totally didn't learn just now for this talk. But this is quite a simple query in a way, right? It's just, it can be answered quite easily, let's say. And you can say, okay, this won't happen in my data set. I don't care why are we even talking about this. But what maybe can happen is a query like the one here. Popular hotels along this road, which I cannot pronounce, I won't try, in Berlin for 5 guests under $200 with 4.10 plus rating. So the idea here is that if your embeddings, if the model had problems with queries like what's this animal or who likes this fruit, they will have bigger problems with a query like this. So they will probably be able to read the road, unlike me, but other problems will persist because this has a lot of different data types, numbers, locations, ratings, which are related to other form of kind of data around reviews and so on. So it gets complex in the real world. So what we're trying to do is we're trying to help dense embeddings, and we think that this war between sparse and dense is maybe too big, so we want to unite the world, in a way, the search world. So dense embeddings do not represent sparse data very well, we know that. However, in practice, what we can see is that signals are correlated. So when a person likes one thing, there is a similar user that also likes similar stuff. So it can happen that similar users like similar things, similar items have similar characteristics like materials or how they're used and so on. And all of this means that actually there is some item interaction, correlation, and this adds info. So it's not just like pure sparsity always. So we need a unified approach of integrating all of the signals that are, some are correlated, some are not, into one shared representation. So you could say, okay, why not just filter post-process? That is a valid thing to do, and a lot of people do that. However, this adds extra passes, it increases latency and cost, and also in a way we're speaking about search relevance, right? If you're doing this, you're kind of doing some post-processing, which in a way it's fine in your full pipeline, but in a purest way does not kind of affect the relevance. What we want to do is we want to say, okay, let's do one pass where the relevance is good enough in the first step. So we don't want to do post-processing and all of that. We want to not solve the problem after the fact, but while it's happening. And what is our angle to this? We use different encoders that capture different aspects of the data. So structured, unstructured data, categories, numbers, and we combine dense and sparse embeddings into like one single vector that's then mapped into a search space and so on. And in this way, linking it to the paper, we increase effectively the dimensionality, and we can discriminate between nuanced relevance patterns. That's the idea. So some of the stuff that I mentioned from the paper, we feel like this is one way to approach this and provide an improvement. So this is part 2, the reveal what's Mixture-of-Encoders. I'll do a high-level overview first. So it's this, as I described. So you have your data and queries. They're both encoded in the same way so that you can have proper approximate nearest neighbor search and all of that, and the similarity is maintained. So we do some pre-processing, normalization, and so on. There's also parts like around query parsing and all of that. And then we have all the different types of encoders for different types of data. So we have the standard text encoders, but also location stuff, number, images, embeddings. And one reason for doing this is that if you just use a text encoder to encode something as simple as numbers, you will find that the similarity between embeddings does not follow the pattern of normal numbers, which means that, for example, the embedding for number 10 would be closer to embedding of number 15 than 11, just because these appear more frequently in the training data and so on. So it's not quite linear and incremental as you would expect. And this problem is even worse with other types of signals that include also temporal elements like popularity, recency. So it gets complex quickly, so that's why we're kind of dividing this problem and using different encoders, and then we aggregate, weight, normalize, doing a bit of cross-encoding somewhere, and then we have a unified vector representation into one long vector. And the more in-depth overview is this. So we also, I think the key difference here is that we also include user context and situational context. And then we use all of these embeddings, and we've also experimented with different query parsing techniques, as you can see. And the even more in-depth overview is this here, which shows kind of one example of how this works. So we have maybe a description that's a string and another integer. So what we do here is we take the embeddings for both, we normalize so that we have the representations matching, and then we concatenate and put this into a vector DB. We do the same thing with the query, and then we do, as you can see here, the dot product between the query vector and the vector in the VDB, and this gives us this very popular PANS, this ability to include different types of signals. And what you can also see here is that there is a scalar, like number 5, next to the popularity vector. And what you can do is at this query time, you can weight this signal so that you can bias things so that, okay, if you want to bias towards more popular items, going like this, you can easily do that. So that's one key insight with a bit of a rudimentary example. And of course, we use approximate nearest neighbor search at scale. It's not dot product by hand. Okay, now a bit back to the high level. What this means in practice is that you can use all sorts of data, 100% of your data, whether this is in tables, in logs, in different structured or unstructured formats. You can include it, and you can build different stuff, so different use cases. So you can get stuff around, okay, user interaction, everything about your inventory data, or maybe Jira tickets, and then you include this. We have a cloud offering, and then in the end you can do stuff like AI search, personalization, chatbots, even agents. So it's not limited to what you do with it. It's more about you're solving the retrieval problem at its core, and you can do stuff like this, like stuff around product, marketing ops. So you can do purchase trend intelligence and personalized emails even. So it's stuff that are common problems that need solving in retail and e-commerce. You can make them happen. And now for the last part, which is, okay, fine, I get the idea. There was this theory. There's a bit of an angle to it of how things can be improved. Good. But where is the proof for this? Like, how can I make sure that this actually makes sense and it works? Well, we had that trouble in a way, because most benchmarks out there, like the ones I mentioned that even DeepMind tested in their paper, they're text only. Maybe some have now images, but they test text-only retrieval, which in the real world is not always the case. As we showed here, there are locations, prices, numbers, temporal effects. So we felt like we needed to kind of find a way to represent that, okay, we want to test out what can happen in this realistic scenario where the data is not just text. And what we decided to do is to make our own benchmark with what we call metadata-aware embeddings. So all of this stuff that I mentioned that are non-text data, metadata-aware embeddings. I will not go with the full quote from this meme, just for the... and first, so initially we didn't start with the benchmark, we did a few things. So we have an article on this. Basically, we just ran a few experiments and experimented and saw, okay, how can this mixture-of-encoder thing that we're doing, whether it makes sense. So we compared it with like BM25, which struggled with some semantic understanding. Vector search improved the semantic stuff, but then lost the relationship between the attributes. Hybrid and cross-encoders worked well, but this embedding of numeric stuff was a problem. Colbert and those kind of late interaction models, they were sensitive to the query parsing. So we had this indication that, okay, actually we need to do this. We need to build a benchmark. We need to try to make things work. So we built a benchmark on top of this dataset, which is like a dataset with a lot of e-commerce products. And I'll go through a few slides here explaining what we did, what our approach was. And of course, this will be very soon. Some of it is already accessible, but very soon it will be fully public, so you can literally test this stuff, run your own models, and see what happens. So we selected columns like this, so like product name, description, material, style. And the big problem was how to construct this query result pair while retaining what we wanted to retain, this type of multimodal data with different query difficulty. So we had this simple queries, negation queries, numbered queries, and basically we created this whole data set, but we also realized that we also want to test what happens at scale. So we actually have a public benchmark that tests VDBs at scale, how they scale with your data, so you can try that out. We have links in the end. And these are the types of queries used. So we have a simple query. So you can read this through later, but the idea is that we wanted to include this different data types so that we can actually test out what happens in complex scenarios where there is like cheap, popular, and words like this. But how do we make the simple queries go to complex? Because we have this simple and complex queries. We did a few things. So we did a bit of data cleaning. Then we did price generation, where we did use an LLM to estimate the price range. But then, depending on what word was used within that query, like if it was something related to the material, we would apply a weight on top of this price so that it kind of biases, oh, this is gold more expensive, or this is plastic less expensive. And then we did normalizations and expansions. So, for example, if we had words or products like wood recliners, we would enrich this to be like wood recliners remote controlled, because we would have these categories of enrichment that were structured. And this ends up with queries like this, where there is silver pendant lights under this price, need clear glass paneling, unique affordable gray dining linen. So you have all these words that we talk about that includes temporal stuff, popularity, numbers. And we did compete with a few, let's say, popular kind of solutions. We worked with Vertex AI, where all of this kind of what exactly we use, this will be published. We compared to Azure. And we also had this situation where we want to test the query parsing. So if people were doing searches with proper structured data, that would have been amazing. But people actually speak with human language. So there is some gap here that kind of the interface between the actual search and human language, so how this is parsed, that was important. And what happened with some of these competitors, like Azure and Vertex AI, they would kind of have zero results, like no results found, when there was like wrong material selection, for example. We were doing proper parameter extraction, so that was a thing that was also important. But as I said, we will publish this in more detail soon. Azure had this black box that had no explainability whatsoever, and we thought that that was important. And this is kind of our ranking as of now. So this will be on our landing page soon. So these are the things we've tested right now, and we also picked the best results for the competitors, whether like they had different query parameters here and there. So how the parsing was done, we wouldn't like disadvantage them by doing something that they didn't. We really tried to do the best we could with them. And yeah, this is the comparison between like the text-only thing and what we're doing with different encoders for different parts of the data. And this is the performance benchmark, that this is public. And you can have a look at the links and all the details in some of my next slides. We also have this vector comparison table that a lot of you might have seen, where we look at different features of different vector databases. We also do this in production, so we have big clients in travel and hospitality, retail, e-commerce. We also have tech partnerships on the open source side with a lot of these great companies. We also have a blog where we write these things. The thing I mentioned, the intuition around the evaluations came from one of these tech articles, and we also have some Maven courses with our CEO, which extend on these concepts in more details. And we have, I don't know if I mentioned this, but we're open source. You can actually have a look at this repo and test things out. There are a lot of notebooks, give us stars and all that, and issues. And this is these are some useful links that you can have a look at. So this is our kind of, we tried to create link tree in a way on our own, and we have this website link that has useful links that you might be interested in. And there we have different links on integrations with LangChain, Llama Index, and we also do LinkedIn office hours. So follow us on LinkedIn, either me, Superlinked, or Daniel's LinkedIn. And this is the place you can talk to us more directly and stay in touch and talk to us about the general space. It doesn't have to be specifically this. We're open to different kinds of discussions. So yeah, thank you. This is me on LinkedIn. Feel free to add me, contact me. And yeah, I don't know if there is time for questions. It's up to you. But yeah, so thank you for listening to my 3-part story. Hopefully it wasn't as... the interruptions kept us alive. So I think it was like, yeah, thank you. Yeah. through adversity, we made it. We made it in the end. We made it to heaven.
Absolutely, yeah. The interruptions expertly handled, so it was dramatic and not a tragedy, I think.
Exactly.
So I'll start with a question from the online audience, because all the others in person can, of course, approach you or Daniel or Ben, who are joining you. So how do you recommend managing changes and updates to individual encoders between different versions while keeping the search service online?
Yeah. So doing that live, I think, is one thing. For example, what we do well is you can. I didn't mention this, but you can use custom spaces. So these encoders that we have, you can use your own custom encoder. So you can supply these vectors from any source that you have, whether it's your own custom non-public kind of encoder, or you do this by hand, or whatever you do, that's possible. Of course, the versioning, I think what we recommend is kind of having some sort of like A/B testing and slow rollout, some sort of like a canary release that you can do when switching up encoders, but you have the ability, you have the freedom and functionality to actually do this. And I guess, yes, in production, it's highly dependent on your use case, but I would recommend something like this.
Thank you. Do we have? Yes, we have.
So kind of question on the practicality of things. I mean, I get that this is great for personalization, especially in e-commerce, because you can in real time just adjust the weights and add some sort of personalization vector and so on. But that comes at the cost of adding dimensions, right?
Yeah.
So have you done some, I guess, nice graphs or whatever about how this affects the overall cost or like the size of volume of data? Because especially if you add categories and stuff like that, that adds a ton of like discrete like value dimensions. So your space just gets huge, and you have to pick between blowing up your infra costs, or you have to sacrifice some dimensions on the underlying text model.
Yeah.
And I guess the second part to it, sorry to make it like a two-part question, is I find like time and recency space kind of tricky, because recency kind of naturally decays over time. So would you go in and like re-index 50 billion articles on Zalando or whatever?
Yeah.
How do you deal with time?
Yeah. So basically, I think two parts. You can have a look at some of the stuff on how things scale. Of course, the benchmark that we have, the external one, that's something to keep in mind, and we have kind of the dimension of the vectors there. So I think that would be a great resource. Maybe we can also give you like later specific data on what our latency is at certain scales. And yeah, with the recency space, I agree, and we're actually doing like an update on the recency space that we use some form of like Fourier transform encoding that kind of does this a bit better, where you don't have to recalculate the recency embedding. But yeah, in a way, this is a bet. So we think that, okay, if you flip this the other way, then you would have to, let's say, hypothetically, right, you either have one very long vector or you have a lot of them shorter ones. So you kind of, if you want to represent the data in the same, let's say, way and with the same context in mind. So in a very extreme use case, you either have a lot of vectors or one that's very long that has all the stuff in there. So we kind of bet on that and think that this scales better, because you have one vector that's very long and then you can do weighting instead of having a lot of shorter vectors when you can kind of scale and do GPU optimizations and all of that. But yeah, we can talk to you about specific stuff, because I don't know the latency numbers, but thank you for the question.
One question from the online audience. Great talk. What kind of encoders would you recommend for location, category, popularity, etc.? How are they trained or learned? It goes a little bit in the same direction, right?
Yeah. Well, so for example, you can look at our repo also. So all of these are implemented there. But we do different things for different encoders. For example, I won't go into all of them because it's like a separate talk maybe. But for example, with numbers, we do some sort of like polar coordinate remapping so that we can kind of maintain this let's say, the steps of how numbers properly increase. So it's like it's not, so not all of the encoders are like, oh, we took this fine-tuned model and we just do that. We also do some like smarter data engineering stuff in the background. So it depends on which encoder as to how it works. But yeah, I think the open source repo is a great place to do this, to have a look at the specific ones that they're interested in.
Great, thank you. And now, last question.
Thanks for the talk. I'm coming from a domain that's similar in a way to this e-commerce example. And we are doing search for companies description, basically for companies, and we're working with descriptions of those companies. In this case, you usually have information like location and some other parameters like, okay, we are the best or whatever. But let's take locations as an example. What's your take of how can we deal with these components of those unstructured descriptions? Shall we do pre-normalization if we use, let's say, your solution, or we can put everything in and your system takes care of it in the final vector?
So when you say put everything in, and you mean like have your own custom encoder?
No, imagine the raw data.
Okay.
It can be like any type of description, but we know there are some key components like location and a bunch of others. Right.
Yeah, so the way we work at this moment is that, for example, you have totally raw data. We have like forward deployed engineers which would look into that specific case and be like, okay, we can pre-process this in a certain way and then feed it into kind of what we're doing into the in where Superlinked starts, let's say. So we don't have, for example, like a specific way of parsing the data. It's more case by case. So as part of what we're doing, it's mainly the retrieval part and that part where you said, okay, now once we have the data, how can we properly encode location? How can we map the space and so on, so that you get that relevance and you can do stuff like, for example, give me the top hotels along Route 66 in the US, let's say, or some other stuff that are related to a location, but not in the most simple way. So yeah, I think we can talk about that, but it's not a part of the library, but we do it, yeah.
Okay, excellent. Thank you, Filip.
Thank you.